Welcome to this video, and I hope you're all well and ready for an interesting topic today. We're going to look at energy and momentum in special relativity. This is going to be a bit of a basic video, a bit from the start, but perhaps needed in the playlist as it currently exists. Anyway, so energy and momentum are central concepts in special relativity, and they are tightly linked through the framework of four vectors, which allow us to express physical quantities in a way that is invariant under Lorentz transformations. Now, this introduction covers the relativistic definitions of energy and momentum, how they are connected through the four momentum, and the famous relationship between energy, momentum, and mass. So having said all that, let's make a start. We'll go over here. Next one. And four vectors and Lorentz invariance, because one of the first things you'll encounter with relativity is four vectors. So let's just start from the basics here. So in special relativity, space and time are unified into a four-dimensional space-time, and physical quantities are often described using four vectors. So momentum, position, velocity, and so on. These things can take on four-wave vectors and so on. They can take on this four-vector form. In Newtonian mechanics, we used to just have three vectors, but with relativity, that extra time component there matters as well and must be included because space and time are connected. So a four vector, just a general one, capital V mu, representing the components. In this video, I'm just going to work with components. I'm not going to express basis vectors as I normally do in the videos. I'm just going to work in components only. Often, as you see in many sources, textbooks and elsewhere, we often just deal with the components only. So that's what I'm going to work with today. But often in videos, I like to include the basis vectors as well, just for completeness and to give what I think is an overall picture. Anyway, so a four vector, capital V mu, in Minkowski space-time consists of components related to both spatial and temporal quantities, I should say. So V1, V2, V3 are the spatial part, represented as capital V, a three vector, whereas the whole thing here is a four vector. And notice the index is up here in the upper contravariant position, all right, starting with 0 for time, and then 1, 2, 3 for the spatial components. So V0 time component related to energy or temporal intervals, and V, capital V here, the three vector, V1, V2, V3, represents the spatial components related to momentum or spatial intervals. The metric of spacetime is defined by the Minkowski metric, eta mu nu, which has the form eta mu nu is this. Okay. Now this is what gives us our distance, our magnitude in relativity. In general relativity and curved space-time, these components won't be constants. Well, it can be constants, but can also be functions of coordinates. Okay, but in the flat space-time and Minkowski space-time, which is Euclidean plus time, we're going to have these are just constant. All right, so this allows us to define the invariant interval, meaning the same for all observers, Minkowski norm for any four vector capital V mu as V covariant mu, lowered indice times that. Okay, we're going to, and I have shown in other videos how this comes about using the metric to lower components and so on, and how we can find the magnitude squared. Okay, so I rely on a little bit of foreknowledge here. So anyway, to compute this lowered indice here, we've seen this V with the upper indices on the previous slide. So to compute this, we use the metric to lower the index. So V lower mu, covariant mu, this is a covariant component, is the metric eta mu nu times the contravariant component. Okay, in that case, the metric here raises and lowers indices, as I've pointed out in many other videos. So here's our metric, here's our four vector here, and lowering that gives us this row vector here. Okay, that's the point here. Now, the product of these two is the Minkowski norm, which is this object here. So in general, for any four vector, we are going, let me just remove that actually. For any four vector, we're going to have, when we work out the magnitude squared of the 4 vector, we get this object here. That's the magnitude squared. Take the square root of it and you get the magnitude of the 4 vector then. This quantity is Lorentz invariant, meaning it has the same value in all inertial reference frames. All right. Now, for momentum. The for momentum, P mu, has a contravariant component mu, of a particle combines the particle's energy and 3 momentum into a single 4 vector. So here's the energy part, the time component, which is the energy over c, the total energy. Here's the spatial part. Right? This is given the bold letter here, or it can have an arrow above it. It could be a P with an arrow above it, or bold. It just indicates the 3 vector. They're the 2 usual conventions for doing that. To express it in this more compact form. E is the total energy of the particle, which includes both kinetic and rest energy. P is the spatial momentum, the 3 momentum. Okay, 3 spatial components, hence 3 momentum. C is the speed of light. The Minkowski norm of the 4 momentum vector is then given by, let's repeat the same process before. We had that row vector here multiplied by column vector, and that gives us this object as we saw on the earlier slide. Now that can be more succinctly expressed as minus E on C all squared plus the absolute value of the 3 momentum vector squared. So the 4 momentum of a particle mass m is given by P mu is m times u mu, where u mu is gamma times this vector, which is C u1, u2, u3. I've expressed it like this, not because it's a row vector, but just because it saves space doing it that way. But think of it as a column vector. That's the particle's fall velocity, and its magnitude squared is u mu. This, again, is minus c squared. I have covered that in another video. I'm not going to go through it here again. I'm just going to quote the result. So the magnitude squared is minus c squared, where I've used the metric minus 1, plus 1, plus 1, plus 1. All right. And on this channel, it's the only metric signature I use. I don't use the other one that you sometimes find in some textbooks, which is the opposite. Right, the time component is positive and the spatial components are negative. Okay, there's 2 different metrics, signatures, and you need to be careful when you're reading material which one you're working with. All right, so the magnitude squared of the 4 momentum is minus m squared c squared, because if the magnitude of the 4 velocity, magnitude squared, sorry, of the 4 velocity is minus c squared, then each p has m times the 4 velocity. Just like in Newtonian mechanics, it's m times the 3 velocity. Mass times 3 velocity. Okay, so the magnitude squared of the 4 momentum of a particle is minus m squared c squared. Okay, except for the case of massless particles like photons, we'll come to shortly, giving us this object here, which is this, is equal to minus m squared c squared. All right, so this final result here. All right, let's move on. So for a particle with rest mass m, when I say rest mass, I should be careful there because it's a bit of a discredited concept you should be aware of now. Mass is invariant. Okay, you'll still find reference to rest mass, and they just mean the mass in the rest frame. All observers agree on the value of the mass. It doesn't change with according to observers or anything of the sort. It's an invariant quantity. So it's a bit misleading to use the term rest mass because there is only one value for the mass. All observers agree on it. This norm is invariant, leading to the important energy momentum relation. E squared is p squared c squared plus m squared c to the 4. This is one of the most fundamental relations in special relativity, connecting the energy, momentum, and mass of a particle. All right, relativistic momentum. The relativistic 3 momentum p, remember the 3 spatial components, not the time component, is related to the velocity of the particle v, that's its spatial velocity again, and its energy, or gamma factor gamma, via the following relation. P is gamma mv. All right. Now, if you're at rest with respect to the particle, gamma will be 1. So, sorry, let me just do that again. Where gamma is the Lorentz factor, as defined by gamma as this object here, okay, which I've covered in previous other videos. But if you're at rest with respect to the mass, then v is 0 and gamma is just 1, and you just have m times the spatial velocity, spatial components. All right. Point of this is that this can be very large. This can get very large for higher speeds. The closer you get to the speed of light, the greater is the gamma factor, as you'll see shortly. So for a particle moving with velocity v, the relativistic through momentum becomes much larger than in classical mechanics as v approaches the speed of light because of that gamma factor. The total energy E of a particle in special relativity is given by E as gamma mc squared, where gamma accounts for the relativistic effects due to the particle's motion. Now, we can make an approximation of this thanks to the binomial expansion. So we'll approximate gamma using a binomial expansion, where for a binomial expansion, x is much less than 1, then the expression 1 plus x to the power of n is approximately 1 plus n times x plus some higher order terms. So for v much less than c, then v squared on c squared would be much less than 1. And so our gamma factor here, which was gamma is 1 over the square root of all that, or all of this to the power of negative a half, is then approximately 1 plus minus a half. Remember the n is minus a half here, times x is v squared on c squared. And so you end up with 1 plus a half v squared on c squared. And when we put that back in here, we've got an m there, and we've got a c squared. When we take this result here, replace it with the gamma here, then we have this result times mc squared, which can be written as, so we can approximate the energy according to E as gamma mc is approximately mc squared plus a half mv squared plus higher order terms. Now the first term, mc squared, is the rest energy, right? That's the energy measured in the rest frame at rest with respect to the particle. And the higher order terms represent the kinetic energy. At low velocities, non-relativistic limits, so you're getting very low, a couple of percent the speed of light or less, which is quite substantial still, the energy reduces to the familiar form E equals mc squared plus a half mv squared, where the second term is the classical kinetic energy. Massless particles, photons, and others. For massless particles like photons, the rest mass m is 0, and the energy momentum relation simplifies to E is just pc, p times c, p is the momentum, c is the speed of light. Because remember we had E squared was a p squared c squared plus m squared c to the power of 4. Well, when m is 0, that second term here drops off, and then you're left with E squared equals p squared c squared, which it just gives you E square root both sides, gives you E equals pc. So this indicates that the energy of a photon is directly proportional to its momentum, and it always travels at the speed of light. All right, so the form momentum of a photon, p mu, is still E on Cp, where E equals absolute value of the 3 momentum times the speed of light. All right, a couple other points for this introduction here. Conservation laws and special relativity, energy and momentum are conserved quantities. Not true in general relativity. This holds true in all inertial reference frames. For example, in a closed system, the total form momentum, p mu, of all particles is conserved. In a closed system, just as in classical Newtonian mechanics, right? Total momentum before is equal to total momentum after. In a closed system, it's conserved. This conservation law applies to both collisions and decays of particles. The invariant mass m of a system is an important concept in relativity. This is the invariant mass. For a system of particles, the total form momentum, we'll call that capital P mu, that's the sum of them all, is the sum of the form momentum of all the particles. So capital P contravariant components mu is the sum of all the form momentum of the particles involved, for I being the number of particles. The invariant mass of the system is given by the norm of the total form momentum. So the invariant mass m squared is the magnitude squared of the form momentum for the system, for the whole system. This quantity is invariant under Lorentz transformations and represents the invariant mass of the system when viewed in the center of mass frame. All right, relativistic kinetic energy. The kinetic energy of a particle in special relativity is the total energy minus the rest energy. The total energy is the total energy E minus the rest energy, mc squared. And in the low velocity limit, this reduces to the classical kinetic energy. All right. Now, example, let's just a couple of basic calculations just to Wasn't even sure whether or not to include this, but anyway, I'll put it in. This is an introductory video for special relativity, which I felt was missing from the list. Now, a proton is moving with a speed 0.8, the speed 80% the speed of light in a straight line. Proton's mass is 1.7 times 10 to the minus 27 kilograms. C we take as 3 times 10 to the 8 meters per second as an excellent approximation. We will calculate the following: the relativistic momentum of the proton, the total energy of the proton, the rest energy of the proton, and then we'll verify the energy momentum relation, this one here. So first we'll do the Lorentz factor. Gamma is 1 on v minus 1 on square root of 1 minus v squared and c squared. So that's 1 over 1 minus 0.8. If you put for the v here 0.8c and then square it, you get 0.8 squared times c squared over c squared. The c squareds cancel out. You're just left with 0.8 squared. 1 over square root of 1 minus 0.64, which gives us this value here. All right, next one. Calculate the relativistic momentum P. P is gamma mp, m subscript p, the proton, times v, its spatial velocity. So we get this times this. Gives us this many kilograms meters per second. We'll calculate the total energy E, gamma mpc squared. So again, gamma is this value here to 4 decimal places, times all that, times that squared, which is this, the 4 decimal places. Calculate the rest energy, which in this case I'll call E subscript 0. E subscript 0 is m subscript p c squared, so that times that squared gives us that value. And what I'm going to do after that then is verify the energy momentum relation. So we're going to have E squared is this, so putting all this information in, p squared times c squared plus m squared times c to the power of 4, we get this object here, which in turn, if we take the square root, because it's a squared here, gives us 2.504, the 4 decimal places, times that. And this result shows that the energy momentum relation agrees with the total energy, okay, or the relativistic energy of this, subject to rounding errors. All right, so that's it for this video. Thank you for watching. I hope you find that informative or useful in some way. If you do, or even if you don't, please tick the like button if you will. That helps me out quite a lot, I think. And subscribe if you will. Okay, thank you very much. I wish you all well. I hope you have a good day wherever you are, and I look forward to seeing you in the next video. So again, if you will, please click the like button and subscribe if you will. Thanks again. Take care.